Hello and welcome to your stats warm-up. So let's see what we got here. Power companies severely trim trees growing near the lines to avoid power failures due to falling limbs and storms. Applying a chemical to slow the growth of the trees is cheaper than trimming, but the chemical kills some of the trees. Suppose that one such chemical would kill 20% of sycamore trees. The power company tests the chemical on 250 sycamore trees. Consider these an SRS from the population of all trees. All right, so what the problem is giving us is it's giving us a sample size. And the way it's saying that one such chemical would kill 20% of sycamore trees, it's basically giving this as our parameter. All right, so the true value of this, chemical killer is 20%. So it says, what are the mean and standard deviation of the proportion of trees that are killed in samples of 250 trees? So this is basically asking about the sampling distribution. All right, if we were to take samples of 250 over and over and over again, what would the mean percentage of trees dying be? All right, what would the standard deviation of percentage of trees dying? So what we learned last class is that the mean of the sampling distribution, so the mean of p hat, is equal to the population parameter, p, which the problem gives us as 0.2. All right, the standard deviation of p hat is equal to the square root of pq over n. All right, we know that p is 0.8 because the problem gives it to us, which means that q must be 0.2 because those add up to 1. And the sample size is 250, also coming from the problem. So 0.8 times 0.2 divided by 250, take the square root of that. We end up with 0.0253, we'll go with. So equals 0.0253. Now, B says calculate the probability that at least 55 trees are killed in a sample, so 22% of the sample. So this is where we start breaking out our NCDF, and we say, all right, what are the odds of getting 22% or higher when the mean of our sampling distribution should be 0.2, and the standard deviation of our sampling distribution should be 0.0253. All right, so again, we would go to our distribution menu, which is second vars. There's our normal CDF, 0.22, 9999, with the mean expected to be 0.22 and the standard deviation 0.0253 on this one. So 0.22, 999, and then 0.0253. And we basically get, wait a second, never mind. Calculate the probability that at least 22 are, all right, here's where I made a mistake. All right, 22 to 999, that's fine. I typed in my mean as 0.22. I should have typed in my mean as 0.2, so my bad there. 0.2, 0.0253, these numbers are feeding in down here. I just didn't type it into my calculator right. So that gives us an answer of 2146. All right. The company conducts their tests and find that 80 trees die, 32% of the sample. What do you think this says about the claim that the chemical only kills 20%? Calculate a probability to support your answer. All right, so everything we just did was based on this number being true. All right, so they went out, they did their sample. They saw that 32% were dead. So the question we're asking is, what are the odds of getting 32% or more dead, assuming this is true? Because assuming 20% is true, then we know the standard deviation should be 0.0253. All right, so let's see what the odds of that are. So 0.32 this time to 9999. Whoops. 0.32 to 9999 when our standard deviation and all of these other things stay the same. So the mean is still 0.2, the standard deviation is 0.0253. All right, Notice that we've got an e to the negative 6 there, so that's really 0.1, 2, 3, 4, 5 zeros, 1054. So super unlikely. All right. So given that getting a sample statistic of 0.32 when n equals 250, because again, all of this is based on this assumption, this sample size. If you change either of these things, then these calculations change, which changes our probability. So given that getting a sample is very unlikely, it seems probable the chemical is more deadly than advertised. All right, so we got this claim that it killed 20%. We went and did our own study. We got 32% of dying. We know there's going to be some variability. We know it's not always going to work out to be 20%. That's the nature of collecting data. But what were the odds of getting something as high as 32%? They were really, really low, which seems to suggest that they're lying about the, proposed lethality of our item here. All right. So moving on. Suppose I retire from teaching and open a casino. Given what you know about my character, you're a little suspicious on whether my games are fixed. You decide to show up and test my dice. You decide to roll a fair six-sided die 60 times and record p hat, the proportion of times that a 1 or 2 is showing. So what is the mean of the sampling distribution of p hat? So again, we do our test. We might not get exactly 1/3, right? Because again, there's 6 sides, 1 or 2. You'd expect to get about 1/3, but in an individual sample, you might get more, you might get less. What this is asking is when you take lots of samples and you average all of those values together, the mean of all of those proportions, it should work out to be the true value, which in our case we know is 2 out of 6 or 1 out of 3. Now, the next question is, what is the standard deviation of the sampling distribution? All right, so that's where we're using our PQ over N. So our P is 1/3, which means our Q is 2/3, and the problem tells us that we're doing it 60 times. So that would be our N. All right, so again, we take this into our calculator, 1/3 times 2/3 is right there. Divide that by 60, take the square root of that, and we get 0.0609. Right, so there's the mean of our sampling distribution. There's the standard deviation of our sampling distribution. C says, describe the shape of the sampling distribution. Justify your answer, aka test the conditions. All right, so there's a couple of conditions we've learned about. One is the 10% condition, which really relates to sampling without replacement. And it affects your ability to use the standard deviation calculation. All right. Now, this one doesn't really apply in this situation because we're just rolling dice. There is no population of dice. And there's no idea of replacement. Each die roll is totally independent. So we don't really have to worry about that one here. The more relevant one, and this is the one that matters for this situation, is the 10 success, 10 failure condition, because this is the one that deals with normality. All right. Now, for us, we find that by doing n times p and n times q. All right. N was 60, p was 1/3, n was 60, q was 2/3. So this one's going to work out to be 20. This one's going to work out to be 40. All right. Since both are above 10, we can trust the sampling distribution will be normal in shape. All right, and I'm using the statistics version of the word normal there with a capital N, like normal curve, bell curve, not just like normal as in like the English version. All right, suppose that when you actually roll the die 60 times, you get 30 rolls of 1 or 2 for a p-hat of 0.5. Am I a dirty, rotten cheat? Justify your answer. So that's basically asking, what were the odds of getting 50% or higher when we were expecting to get 1/3 and the standard deviation was the 0.0609. All right, so we go to NCDF, we say 0.59999. We were expecting a mean of 1/3, and you can just type it in as 1/3. And our standard deviation was 0.0609. And the odds of that happening were only 0.0031. All right. So based on the probability, it appears the dice are not fair, because there was only a 0.3% chance of that happening. I mean, it could have happened, but it was so unlikely that we're better off saying that the dice are probably not fair. All right, last one here. With the rise of this new thing called the interweb, you have to wonder, are attitudes towards shopping changing? Sample surveys show that fewer people enjoy shopping than in the past. A recent survey asked a nationwide random sample of 2,500 adults if they agreed or disagreed with the statement. I like buying new clothes, but shopping is often frustrating and time-consuming. All right, in this survey, 1,520 agreed. Suppose, in fact, that 60% of all U.S. adults would say agree if asked the same question. All right, what is the sample proportion of U.S. adults who agreed with this statement? All right, so we've got a few things going on here. This would be our parameter, right? Because they're telling us that if we were able to talk to 60% of all adults, or if we were able to talk to all adults, 60% would say agree. All right, now where did that number come from? Again, it's in the problem. You just have to accept it. We probably couldn't actually calculate this number, but we've got it. All right, this 2,500 is our N, and this 1,520 is our sample result. So this says, what is the sample proportion? That's asking for p hat, which is our 1,520 over 2,500, which works out to be 1,520 divided by 2,500, 0.608. And so that's our sample proportion. It says, if in fact the proportion of all U.S. adults who would agree with a statement is 0.60, what is the probability that the proportion in a random sample of 250 adults is as far from 0.6 above or below as the results of this survey? All right, so that's basically saying, what are the odds that it's either you know, 0.008 above or 0.008 below. All right. Now, to answer this question, we need the mean of our sampling distribution, which we know is the population parameter, which the problem gave us as 0.6. We need the standard deviation of our sampling distribution, which is the square root of PQ over N. All right. So in this case, we use the population parameter of 0.6. We use the Q of 0.4 because those are always going to add up to 1. And our sample size was 2,500. All right, so if we do 0.6 times 0.4, 0.6 times 0.4, divide by 2,500, and then take the square root of that, we get a standard deviation of 0.0098. All right, so there's our standard deviation. Now, to answer the question here, we're going to do an NCDF, and they said as far above or below. So we're going to go 0.08 above 0.6, and we're going to go 0.008 below 0.6. All right, so I typed in. We're basically doing an NCDF from 592 to 0.608. All right, we're asking what were the odds of being this far from the mean in either direction if this was the true value and this was our standard deviation, which again is based on our sample size there. So 0.0098. I can go over to normal CDF, 0.592, 0.608, 0.6, 0.0098. Paste that in there, and we get 5857, basically. 0.5857. So, this is well within kind of normal here. 60% of the time you're going to be inside of that range anyways. So nothing, nothing too crazy going on there. Now, if you wanted to know the probability that it's above that 0.08, then you're looking at an NCDF from 0.608 to 9999. And then you'd have to do the same thing in the other direction and add those together. So negative 999 to 0.592, 0.6, 0.0098. All right. So this is the probability of being in that range. And if you added these two together, this is the probability of being above or below the range. Now, I could calculate this directly. All right, I could put this into the calculator, put this into the calculator, add them together. But I also know it's just going to be 1 minus this, all right, because the entire curve has an area of 1. So if I do 1 minus this answer here, I get 0.4143, all right, which is the same thing I'd get if I did one of these. All right, so if I went to normal CDF, did 0.608 to 9999, keep all that other stuff the same, it gives me that, but it's symmetric. So if I were to double this, all right, these two are going to give me the same thing anyways, and I get right back to that 4143 that I had there. All right. So hope this was useful. If you have any questions, just let me know and we'll go from there. But basically, the gist is the same. You find the mean of the sampling distribution, which the problem almost always gives you. You find the standard deviation, which you have to calculate, and then you use both of those in an NCDF to answer a question. All right. Sometimes they'll ask whether conditions are met. Just remember that the 10% condition is for sampling without replacement, and that deals with the standard deviation. The 10 success and 10 failure condition deals with, is the shape of the sampling distribution going to be normal enough? And then there's also like the randomization one, that things should be randomly selected. And there's also the independence criteria. So like the the people in your sample shouldn't have some sort of connection or some sort of thing where one is influencing the other. All right. There should be sort of independence between the participants there. All right. So hopefully this was useful. Again, let me know if you have any questions. Otherwise, have a great day.